Good afternoon, everyone. I'm Rushikesh Ghatpande. Since 2018, I have been working in the network virtualization and microsegmentation space at VMware, now Broadcom. And typically, our large-scale customer deployments consist of 100,000 workloads. We at VMware by Broadcom, we provide all the underlying infrastructure software to help them run these workloads, because these workloads are responsible for the customers to keep their businesses moving, running seamlessly. So let's say a database VM comes up or an application container comes up. Whatever policy that the customer has decided for a database class of VM or an application class of container, those security policies, network rules, they have to be immediately applied. As a result, both our customers and we need a central management plane with a real-time view of the customer's inventory in the data center. Because if there is a workload which we cannot see, we are not able to secure it. Today, I'll share how we built a reliable inventory sync service which does just that, one that has been running for years with zero escalations. So let me explain what we were trying to build. We were building a management plane. It needs to know about every workload in the data center, every VM, every container, 100,000 of them. So the workflow would go something like this. These workloads, they would register with the management plane. They would push their configuration details. And based on the policies configured by the users, we would push down the security policies and network rules which match the workloads, the configuration. So 100,000 workloads, each maintaining a persistent connection and talking to one management plane. Now imagine something happens, a network blip, a cluster restart, a data center power event, and all of the workloads, they try to reconnect at once, and your management plane cannot keep up. What would you do? Well, one answer is you scale up your management plane. You have auto-scaling enabled in it. You let the elastic infrastructure handle the spike. Another is you add jitter. You have the workloads, you randomize the reconnect times for the workloads so that you space out the initial connection spike from a few seconds to a few minutes. But randomization is a very poor way of having deterministic outcomes. And second is you may control the thundering herd of connections by randomizing the reconnect times. But when these workloads, they connect with the management plane again, they have to send over their full configuration because the management plane is not aware what has changed in the time when the VM was not connected. For example, let's say 2 new NICs were added, and now you need to protect these 2 new NICs. So adding jitter, it helps with manage the thundering herd of connections, but it really doesn't help with managing the thundering herd of data. Add to it, we had more constraints. We only had 1 GB of memory for handling these 100,000 workloads. And we couldn't scale our inventory service horizontally or vertically. Now, our challenges are very different to a cloud-based solution. Our software goes into customers' on-prem data center, and we have to extract as much value from the resources offered to us as we can. We can't just scale out in their data center, because every gigabyte that we use is a gigabyte that they cannot use to run their business. And especially now with AI workloads, you know how precious memory has been. So for us, handling such scale challenges means approaching these problems differently. In this case, it was how do we manage the thundering herd better? And this is the evolution timeline of how we did that. Our inventory sync protocol, it evolved over 2 years of hitting real production scenarios and solving for edge cases. I'll break down the evolution timeline. First, right from the onset, we realized that we just won't be able to handle 100,000 connections with just 1 GB of memory. The math, it just doesn't add up. Hence, we had to think of a different topology. We had to relook at the architecture itself. We came up with a tiered architecture. Our management plane, it had a lot of verticals as we started developing more and more features. And then we decided that all these verticals, they should share the transport between them to further reduce the connection count. Now that we had a tiered architecture, we needed some form of a sync protocol. At scale, that sync protocol broke. We had to introduce some form of flow control. We did it through a handshake stage. We carefully paid attention to all our config parameters. We used real measurements to configure all of them, which helped us a lot as we scaled. Also, because we were having a shared transport, we realized that just because the servers are connected with the management plane doesn't mean the applications are ready. So we distinctly identified a connection being established from an application being ready through an app init stage. And thus, a 5-stage sync protocol was born. It took 2 years for this protocol to mature and for us to get it right, but it has been running without escalations for the past 4 years. Now, let me break down all the evolutions one by one. So our first evolution was coming up with a 3-tier architecture. Now, in this architecture, the workloads, they didn't register directly with the management plane, but they were managed separately. So up top, I have drawn a tier 0 management plane. In it, I have shown 2 services, inventory service and config service. In reality, there were a lot more verticals providing a lot more feature. And this is where the customers come to have a unified view of their inventory and configure universal policies across their workload. At tier 1, we have our servers. So now we decided rather than workloads coming and registering with the management plane, it would be the servers on which these workloads reside. They would be our first-class citizens, and they would be the ones who would be registering with the management plane. And these tier 1 servers, they would be responsible for informing all of the inventory that is running on top of them. So for inventory service, it had a counterpart agent running on all the servers called inventory agent. And this inventory agent was responsible for aggregating the inventory running on that server and informing the inventory service. Tier 2 was where the workloads lie. Now they were discovered resources on management plane. They were no longer first-class citizens. And one more point I wanted to bring up was, as you see, the inventory service is connected with all the inventory agents on the servers. And similarly, the config service is connected with all the config agents on the servers. So if you have 1,000 such servers and let's say 5 verticals, then we had reduced our incoming connection count from 100,000 connections to say 5 into 1,000, which is 5,000, which was very helpful for us to get started and scale better. But then we realized that, hey, even 5,000 connections is a lot, especially as we are going to keep on adding newer and newer features. That's when we decided to come up with a common messaging layer. Now, you can see here, there is a management proxy on the management plane side. All the services which sit on the management plane, they talk to their counterpart agents on the server through this management proxy. And similarly, all the communication on the servers, it goes via the server proxy. The advantages of separating out the messaging layer were twofold. One, we knew that as we scale even further, we are going to need more connections. Second is all the messaging related complexity when it comes to, say, transient disruptions or just handling the connection, just the connection handling. It was taken care by the messaging layer itself without the applications needing to worry about it. And in the future, we also, we started with a custom RPC and custom proxies. But in the future, we were also able to replace them with highly performant Envoy proxy and gRPC while having very little impact on the verticals which sit behind them. And in this process, we had reduced the number of connections again from 5,000 to just 1,000 because now there was just one connection from every server to the management plane. That also helped us scale better as we added more and more features. But now with a tiered architecture, we needed some form of a sync protocol to sync and keep the inventory consistent at all the tiers. And this is how the first sync protocol looked like. It was pretty straightforward. The servers, they would establish connection with the management plane. They would aggregate all of the inventory data they are responsible for, and the inventory agent would send this entire data. We call it full sync. Once the full sync is ingested by the management plane, any subsequent updates, let's say a VM moving from one host to another host, a new NIC getting added, they would just come in as delta updates. So just a standard 3-step FSM, you establish connection, you have full sync followed by delta sync. And anytime the connection gets interrupted, you just go, you go in circle. And of course, at scale, this failed because what would happen is if management plane restarts, it would establish connection with all the servers. All the servers would immediately start sending over their full sync data. The management plane would get overloaded, it would crash, and it would again restart, it would again establish the connection. So it would just get caught in this sync storm. And it would take quite a bit of time for things to stabilize. So that's when we knew that we need some form of a flow control, which brought in the third evolution, which was the sync handshake stage. In this stage, the servers on connecting to the management plane, instead of sending over their entire data, they would just check in with the management plane on if they could send their data. So the workflow started looking something like this. Servers would send a sync request. The management plane would evaluate the system load it was under. If it was under too much load, it would just say that, hey, I'm not ready. The servers would back off again. They would send a sync request again. This time around, if the management plane thinks that, hey, it will be able to ingest this newly coming data, it would send a sync ready message. That's when the servers would consolidate the entire data and send over the full sync data. So it turns out that the idea of having flow control through a sync handshake stage was the correct idea. However, the implementation needed hardening. Because what would happen is we had not really handled the thundering herd just yet. When, let's say, 10 servers were sending over their full sync data, all the other servers would just keep on checking with the management plane, asking, hey, can we sync our data? Can we sync our data? And all of this noise was just needless. We could reduce it. Another thing was, let's just say on the same lines, if there was a server 11 who was not served because the management plane was loaded, what would happen is it would back off, and then there would be other servers who would come in ahead of it, and they would be served first. So the system was inherently unfair, and especially if you had a crash loop backing servers, which would just crash and come back and connect and ask to be synced, they would hog over and not allow some of the healthy ones to proceed. So we decided that the Flow control should be in the management plane's hand and not reside with the server. So the management plane, what it would do is it would record the first sync request. It would put that particular server in the queue. So all the servers would have a fixed place in the queue, and they would be served in a first come, first served basis. This system was inherently fair and served us well. One more thing that we did is we carefully relooked all our config parameters. We decided to take a look at all the timeout values, all the strategies, and that helped us immensely. We used real measurements for that. And what we realized is if we have a scale of 1,000 VMs and 1,000 servers, and so having 100 VMs on an average, then we have a lot of config parameters. Here I have just shown 5 of them. All these config parameters are closely related to each other or derived from each other, and we know the why behind them. So for example, what we realized is when given a scale of 1,000 servers and 100 VMs on an average, we are able to handle 50 parallel syncs. So our batch size was 50 hosts. At the same time, we realized that if some of the hosts initially were VM heavy, then we could only handle a batch of 1,024 VMs. So whichever number is hit first, that would be our batch size. We arrived at this number by memory profiling our inventory service. And that's when we knew that, hey, this is a good enough scale given just 1 GB of memory. What we realized is it takes roughly 60 seconds for us to handle all the incoming full sync data from one such batch. And if you just do the math, then when you have 1,000 hosts and you serve 50 hosts in 1 minute, then the queue drain time in total would be 20 minutes. So any workflow which existed on the host side, it would consist of, the timeout values would consist of more than 20 minutes, because the workflows on the host side or the server side, they know that in the worst case scenario, it can take up to 20 minutes for my data to show up on the management plane and me to get some subsequent policies for me to react. That's how we know that the timeout has to be more than 20 minutes. Again, I had mentioned that we had one spot in for every server in the queue. But let's just say that one of those servers, it was a crash looping server and it was not able to fully sync its data. Then after 5 failed attempts, we would quarantine it for an hour and allow all the healthy servers to move through. And we discovered all of these nuances after carefully looking at our config parameters. So tomorrow, if we have to support twice the scale with 50% more memory footprint, we exactly know how to batch things in the worst case scenario, how long will it take for our data to be eventually consistent and us to have an accurate state of the inventory on the management plane side. That's the level of confidence we develop when we really dive deep into our numbers. With all these improvements now, the sync handshake stage started looking a bit like this, wherein the servers, after a persistent connection is established, they would send a sync request. The management plane, because it was seeing the sync request for the first time, it would add that request to the queue. Then there would be a fixed backoff delay of 20 minutes based on the explanation I gave on the previous slide. And it would again send a sync request. At this time around, this request was not even added to the queue because the management plane already had it. It just had not come to process it. Once the management plane would dequeue the request belonging to that server, it would send a sync request accepted to the server. So now it was the management plane controlling the flow. That's when the server would consolidate the entire data and send the entire data as part of full sync. So this particular change in the sync handshake stage helped us get very good control over the incoming herd, and we had in some ways managed our herd. But then we realized something more. Although we had managed our herd, at times, even when the system was not loaded, it would happen that the data is that it is taking 20 minutes for the data to be eventually consistent on management plane side. And it was very hard to explain why that was happening. So that's when we realized that, hey, when the management plane is coming up, the messaging layer is getting initialized first, while the inventory service is still getting initialized at times. So what would happen is, earlier, the connection would be established, but the first sync request which was getting sent, there was no one to really process it. So that sync request would go unanswered because the inventory service was still getting initialized. And then by the time the 20 minutes occur and the second sync request comes in, at that time, of course, the inventory service was up healthy and it could process all the data, and it would take 20 minutes for the data to be consistent. So that's when we realized that, hey, just because we are connected doesn't mean that the inventory service is ready. We have to aggressively check for the readiness of the service itself. So we came up with an app init stage wherein the servers on connecting with the management plane, they would aggressively check whether the backend application, which was the inventory service, was ready or not. And it would check, like the maximum timeout in it was 5 minutes. So we would know within 5 minutes whether an application was ready or not, and then the data would become eventually consistent. So adding this app init stage, it helped us in average case get the time to become eventual consistent down to 5 minutes rather than it being 20 minutes. So this was our robust sync protocol. It evolved from a standard knife sync protocol of 3 steps into a 5-step protocol. First, we used to establish connection. Then we would check whether the applications are truly ready. If the application is ready, then we would have a flow control stage through a sync handshake. And that's when we would send over full sync data. And then the protocol would remain in the delta sync stage, wherein only the delta updates were sent. And these are the payoffs of moving to this particular 5-stage model. So first is it is battle hardened. The protocol, it just didn't come overnight. It evolved over 2 years of real production encounters and solving for edge cases. But ever since we have moved here, we have had 0 escalations in production. Also, over the years, our scale has increased 4 times. We just need to tune the parameters. The central protocol, it has remained the same. Also, as our scale has increased, one reason for the increase in scale is we started supporting new inventory types, and the protocol, it just works fine. We have also replaced tier 1 servers with similar logical entities, and things just seem to be working fine. And above all, the protocol is self-healing, because as long as we know that systems come back healthy, we know that the data that you're going to see in the management plane is going to be accurate, and it is eventually going to converge. These were some of the lessons that we learned along the way. First was that distributed systems have layers, and these layers, the startup sequence is different for different layers. So one shouldn't conflate 2, because that's when you have a lot of silent failures. In our case, it was that we had to separate out transport layer readiness from application readiness. That helped us become eventually consistent faster. Then, as I mentioned earlier, we know the why behind every config parameters of ours. Because if you don't know why a timeout value is set to a certain number, you don't truly own that particular timeout value. Also, you have to design for the worst minute, not the average hour. That's because the resiliency of your system is truly tested in that 1 minute when the world is trying to connect to you. And it also builds the reputation of the software that you built. You will be judged on that 1 minute instead of the whole hour. That's the unfortunate reality. Another point is fairness is not free. Systems are unfair by default. You have a lot of time bad behavior being served first, while patience is usually punished. So if you want to create fair systems, you have to explicitly design for it. In our situation, it was that the loudest clients, the broken clients, were winning over the healthy ones, and we had to design for it. And as I have mentioned, we have increased our scale four times now. And only thing we had to do is just take a look at our config parameters again, tweak them to match the new realities, new resources. We have new SLAs we have promised, and we have not really touched the protocol anytime over the past few years. So these principles helped us get to a robust inventory sync service when we had to support 100,000 workloads with just 1 GB of memory, and there was no way for us to scale. Thank you, everyone. I'll open it up for questions.